let's continue. Okay, let me open the table of content first. Okay, we are on chapter 18, patching instruction here, and the last time we are on section 18.1, a simple example and overview, and now we will read the where are page table store. Okay, let me open that. Okay, we'll take a look at this. This is the representation of the page in the, what is it called, page frame, I guess, or physical memory, right? Okay, and then there is this term physical frame number and virtual page number, the VPN. Okay, and then oh, page table in this. Okay, right. Alright. Yeah, there is a few basic questions about patching. Where are these page table store? What are the typical content of the page table? And how big are the tables? Right? Does patching make the system too slow? This and other beguiling questions are answered at least in part in the text below. Read on. Okay. Where are page table store? Page table can get terribly large, much bigger than the small segment, or much bigger than the small segment table. Okay, or base or bound pair we have discussed previously. For example, imagine a typical 32-bit address space with 4 kilobyte bits. This virtual address split into a 20-bit virtual page number. Again, VPN in this case means virtual page number, and 12 bits offset. Recall that 10 bits would be needed for 1 kilobyte page size. And just add 2 more to get to 4 kilobyte. 10 bit would require 1 kilobyte page size. And just add 2 more to get to yeah, I'm still not sure about this statement, I guess. What it means, just add 2 more to get to 4 kilobyte. 20-bit VPN 20-bit virtual page number implies that there are 2 power 20 translations that the operating system would have to manage for each process, right? That is a lot, I guess, roughly 1 million. Assuming we need 4 bytes per page entry, per page table entry, 64 bytes per page table entry to hold the physical translation plus any other stuff, we get an immense 4 megabyte of memory needed for each page table. Each page table, that is pretty large. Now imagine there are 100 processes running. This means the operating system would need 400 megabyte of memory just for all those address translation. Right. Even in the modern era, where machines have gigabyte of memory, it seems a little crazy to use a large chunk of it just for translation, no? And we won't even think about how big such a page table would be for 64-bit address space, right? That would be too gruesome and perhaps scare you off entirely. Because page tables are so big, we don't keep any special on-chip hardware in the MMU, Memory Management Unit, to store the page table of the currently running process. Instead, we store the page table for each process in memory somewhere. Oh, we don't keep any special on-chip hardware in the Memory Management Unit to store the page table of the currently running process. Instead, we store the page table for each process. Page table for each process in memory somewhere. Let's assume for now that the page table live in physical memory that the operating system manages. Later, we will see that much of operating system memory itself can be virtualized. Oh. And those page tables can be stored in operating system virtual memory and even swipe to this. But that is too confusing right now, so we will ignore it. In figure 18.4 on page 5 is a picture of a page table in operating system memory. See the tiny set of the translation in there. Okay, wait, before we continue, let me read the aside. Aside data structure, the page table. One of the most important data structure in the memory management subsystem of a modern operating system is the page table. In general, a page table stores virtual to physical address translation, thus letting the system know where each space of an address space actually resides in physical memory. Because each address space requires such translation, in general there is one page table per process in the system. The exact structure of the page table is either determined by the hardware of the system or can be more flexibly managed by the operating system, the modern system. Oh, okay. So on the older system, the page table is determined by the hardware. Oh, interesting. Okay. And in the modern system, it is managed by the operating system from the operating system virtual memory. Now I'm kind of curious that operating system has its own address space. Wait a minute. The question is operating has its own address space. Yeah, I'm still not sure. But maybe it has. I mean, operating system also a process, right? In a way. But well, yeah, I'm still not sure yet. Let's continue. Figure 18.4, page 5. Oh, this one. 18. Wait a minute. 18.4 or 5? 18.4. Oh, this one. Okay. Is a picture of page table in operating system memory. See the tiny set of transactions in there. I am assuming this one, I guess. Maybe. Okay. What is actually in the page table? Let's talk a little about page table organization. The page table is just a data structure that is used to map virtual address, or really virtual page number, to physical address or physical frame numbers. Thus, any data structure could work. The simplest form is called a linear page table, which is just an array. The operating system index the array by the virtual page number. Okay, in this case, it is abbreviated to VPN, virtual page number, and looks up the page table entry, or PTE, at that index in order to find the desired physical frame number, PFN. Okay. For now, we will assume this simple linear structure. In a later chapter, we will make use of more advanced data structure to help solve some problem with patching. We will assume this simple linear structure. Okay. In later chapters, we will make use of more advanced data structure to help solve some problem with patching. Okay. So for now, we will use the linear page table, I guess. As for the content of its PTA, the page table entry, we have a number of different bits in there worth understanding at some level. Different bits in there. Okay. A valid bit is common to indicate whether the particular transaction is valid. For example, when a program starts running, it will have code and heap at one end of its address space. When a program starts running, it will have code and heap at one end of its address space and the stack at the other. All the unused space in between will be marked invalid, and if the process tries to access such memory, it will generate a trap to the operating system, which will likely terminate the process. Thus, the valid bit is crucial for supporting a sparse address space. By simply marking all the unused bits in the address space invalid, we remove the need to allocate physical frames for those bits and thus save a great deal of memory. Okay. Figure 18.5. A x86 base table entry. Page frame number. I'm not sure what this means. Is this read and write? Yeah. We also might have protection bits indicating whether the bits could be read from, written to, or execute from. Again, accessing a bit in a way not allowed by this bit will generate a trap to the operating system. There are a couple of other bits that are important, but we won't talk about much for now. A present bit indicates whether this bit is in physical memory or on disk. Oh, interesting. That is, it has been swapped out. We will understand this machinery further when we study how to swap parts of the address space to disk to support address space that are larger than physical memory. Swapping allows the operating system to free up physical memory by moving rarely used bits to disk. A dirty bit is also common, indicating whether the bit has been modified since it was broke into memory. Oh, okay, there's a present bit here to indicate whether this bit is in physical memory or on disk. And there's also a dirty bit indicating whether the bit has been modified since it was broke into memory. Okay. And there's also reference bit, also known as access bit, is sometimes used to track whether a page has been accessed. Oh, a page has been accessed, and is useful in determining which pages are popular and thus should be kept in memory. Such knowledge is crucial during page replacement, a topic we will study in greater detail in subsequent chapters. Okay. Figure 18.5 show an example page table entry from the x86 architecture. Okay, it contains a present bit. Oh, P is the present bit. Alright. And then a read or write bit. Okay. Which determine if writes are allowed to this page. A user or supervisor bit. A user or supervisor bit which determine if user mode process can access the page. Okay. A few bits. PWT, PCT, PAT, and G. That determine how hardware caching works for this page. hardware caching. Okay, an access bit, the A in this one, I guess. A 30 bit. Okay, this one has been modified, right? Okay, access bit and then 30 bit. Okay, and finally the page frame number, PFN itself. Okay, read the Intel architecture manuals for more details on x86 paging support. Be forewarned, however, reading manuals such as this, while quite informative and certainly necessary for those who write code to use such page table in the operating system, can be challenging at first. A little patience and a lot of desire is required. Okay. Alright. We have to take a look at aside this one, so let me read this aside. Why no valid bit? You may notice that in the Intel example, there are no spared valid and present bits, but rather just a present bit. If that bit is set or p equal 1, it means the page is both present and valid. Oh, if not, p equals 0, it means that the page may not be present in memory but is valid, or may not be valid. An access to a page with p equals 0 will trigger a threat to the operating system. The operating system must then use additional structure it kept to determine whether the page is valid, and thus perhaps should be swept back in or not. And thus the program is attempting to access memory illegally. This sort of judiciousness is common in hardware, which often just provide the minimal set of features upon which the operating system can build a full service. Okay. So if the p equals 0, is this related to the, what is it called, the page fault? I've heard that, or maybe read somewhere, maybe in this chapter, that, what is it called? Sometimes we just place a what is it called? A create placeholder, I guess. Sometimes we just create the placeholder for the memory, but did not connect that to the physical memory yet. Is that also what is it? The present bit equals 0 here. Maybe. So when p equals 0 here, it can be that we haven't connect the virtual address with the physical address. Maybe something like that. Or we haven't, what is it called? We haven't allocated the virtual address according to the page table. Maybe something like that. What is it? P equals 0. Is there two condition? There two condition. Two possible condition, like we have the place for allocated memory, but haven't connected yet with physical virtual memory, but haven't connected yet with physical memory, and no placeholder, no allocated memory, no allocated virtual memory. Maybe something like this. Present bit. Okay, if not p equals 0, it means that the page may not be present in memory but is valid, or may not be valid. Is false. Okay. Maybe rather than question, let's make this a statement, I guess. There are two possible conditions, like we have the placeholder for allocated okay. The page may not be present in memory but is valid. So what is it called? The page exists in the page table, but we haven't connect those virtual page number to the page frame, I guess. The possible condition. Let me read this again. The virtual page number exists in page table but didn't have the, what is it called? But didn't have the related page frame number, maybe something like that. This is valid, and then virtual page number, or the virtual page, maybe, yeah, let's call it virtual page number, does not exist in page table. This is invalid. Maybe something like this. So the virtual page number exists in page table, but didn't have the related page frame number. So it is actually valid, but we haven't connected the virtual page to the page frame. And then the virtual page number does not exist. Okay, maybe something like that. Alright. Alright, this one. The program is attempting to access memory illegally. The second scenario here. Okay, paging also too slow. Oh, interesting. With page number in memory, we already know that they might be too big. As it turns out, they can slow things down too. For example, take our simple instruction. Okay, let's just examine the explicit reference to address 21 here. And not worry about the instruction fetch. In this example, we will assume the hardware performed the translation for us. To fetch the desired data, the system must first translate the virtual address into the correct physical address 117. Thus, before fetching the data from address 117, the system must first fetch the proper page table entry from the process page table. I'm assuming is page table entry is the index. Let me double check first. 4 bytes per page table entry to hold the physical translation. Okay. So maybe this is the item in the page table. Something like that. Okay. Fetch the proper page table entry from the process page table, perform the translation, and then load the data from physical memory. To do so, the hardware must know where the page table is for the currently running process. Right, where the page table is for the currently running process. Let's assume for now that a single page table base register contains the physical address of the starting location of the page table. To find the location of the desired PTA, the hardware will thus perform the following function. Okay, virtual address virtual page number max. Oh, write save. Okay. Let's assume for now that a single page table base register contains the physical address of the starting location of the page table. To find the location of the desired VTA, the hardware will thus perform the following function. The location of the desired VTA, the page table entry. Okay, this one virtual page number, virtual address with the virtual page number max, and then write save. Oh, okay. I kind of forgot. Is write save multiply all? Divide, I guess. Okay. Oh, it is division by 2. Okay. Okay, write save, and then page table entry address, page table base register plus virtual page number multiply the size of the page table entry. In our example, VPN max would be set to 030, the hex 30 here, or binary key, this one, which picks out the VPN or the virtual page number bits from the full virtual address. Shift is set to 4 the number of bits in the offset, such that we move the virtual page number bits down to form the correct integer virtual page number. Okay, would be set to 30 or binary this one, the hex 30, or binary number this, which pick out the virtual page number bits from the full virtual address. Shift is set to 4 the number of bits in the offset, such that we move the virtual page number bits down to form the correct integer virtual page number. Okay, for example, with virtual address 21, right, this one, and masking turn this value into this one, the shift turn it into this one. Oh, okay, right. Or virtual page 1 as desired. We then use this value as an index into the array of page table entry point to by the page table base register. Okay, once this physical address is known, the hardware can fetch the page table entry from memory, extract the page frame number and concatenate it with the offset from the virtual address to form the shared physical address. Once this physical address is known, the hardware can fetch the page table entry from memory. Okay, we then use this value as an index to the array of page table entry point to by the page table page register. Okay, when this physical address is known, the hardware can fetch the page table entry from memory, extract page frame number, and concatenate it with the offset from the virtual address to form the desired physical address. From the virtual address to form the desired physical address. Specifically, you can think of the virtual of the page frame number being left shift by shift. Wait. Isn't this right shift? Oh, it's different. Okay. Specifically, you can think of page frame number being left shift by shift and then bitwise or with the offset to form the final address as follow. Okay, the address. Alright. Left shift and then OR. Okay, finally the hardware can fetch the desired data from memory and put it into register EAX. The program has now succeeded at loading a value from memory. To summarize, we now describe the initial protocol for what happens on each memory reference. Figure 18.6 page 9 shows the approach. For every memory reference, whether an instruction fetch or an explicit load or store, paging requires us to perform one extra memory reference in order to first fetch the translation from the page table. That is a lot of work. Extra memory references are costly, and in this case will likely slow down the process by a factor of 2 or more. Okay. For every memory reference, whether an instruction fetch or an explicit load or store, paging requires us to perform one extra memory reference in order to first fetch the translation from the page table. One extra memory reference in order to first fetch the translation from the page table. Okay. That is a lot of work. Extra memory references are costly, and in this case will likely slow down the process by a factor of 2 or more. And now you can hopefully see that there are two real problems that we must solve. Without careful design of both hardware and software, page table will cause the system to run too slowly, as well as take up too much memory. While seemingly a great solution for our memory virtualization need, these two crucial problems must first be overcome. Okay, let me read figure 18.6. Accessing memory with paging. Extract the virtual page number from the virtual address. Okay. Virtual page number what is it called? I think we can think of virtual page number like the index, I guess. So we extract the index from the virtual address. From the address of the page table entry. From the address of the page table entry. What is PTBR here? Oh, page table base register. Okay. Page table base register. Alright. Plus virtual page number or the index times the size of page table entry. Okay. Then we got the page table entry address. Okay, so we have the base register too. Alright. First the page table entry, access memory. Check if process can access the page. If process can access the page. Segmentation fault. Okay. Can access. False. REST exception. Okay. Protection fault. Okay. Access okay. Form physical trace and fetch it. With this instruction. Access memory. Okay. A memory trace. Mmap kah ini bang? No, not necessarily mmap. I mean, I'm assuming you're talking about mmap here, right? I mean, we are learning about memory management, but not necessarily about mmap library here. So no, not the specific mmap, but just the general memory management, I guess. Okay. A memory trace. Oh. A virtual and physical memory trace. Wait a minute. So the point of this section is that we need another, what is it called? We need an extra memory reference. For every memory reference, whether instruction fetch or an explicit load or store, patching requires us to perform one extra memory reference in order to first fetch the transaction from the patch table. I'm assuming this one, I guess. Fetch from the patch table entry. Maybe this one, the extra, what is it called? The extra memory reference. Okay. And then after checking this out, the patch table entry, we can finally access the physical address. Maybe something like that. The real problem. These two crucial problem. Okay. The problem, Wait, did I miss something? What is the other problem? And now you can hopefully see that there are two real problems that we must solve. I think the first problem is this one, extra memory reference. But what is the other problem? Is it the size? We have a number of different bits in there with understanding at some level. Okay. Alright, well, I guess we will continue this on the next session. I will try to figure this out on off stream, I guess. Yeah, we will continue this on the next session about memory trace. So that's it for now. Thank you for watching and see you next time. Bye bye.